Hello and welcome to Chapter 6, Quality of Service. So tonight we are going to go over the different types of techniques that are used by the service providers, or you can do it yourself on the administrator end, on the LAN end, to set up your network so it can set priorities to packets or even frames so that, for example, applications that required to go out the door first, such as voice and video, you can set priority to them. So that's what really quality of assurance means, setting priority to traffic. One way of doing it is telling the router that depending on which type of packets that are coming in, you're going to set priorities to it. So either you can put a little number on, you can flag the number on the packet or on the frame itself, depending on what that number is. If it's, for example, voice, it should go out first. If it is web, it can wait to be last. If it's some financial transaction, that will have less priority than voice, but better priority, for example, than web pages. So by examining the bits on, let's say, the packet itself, you can put them in the queue, which is a waiting area. All right, so there's a software that checks the queue area. If sees anybody in the priority, he has to go first before he takes anybody else and place them on the trunk, because all of this connections, the router has one connection to the outside, the trunk. So only one guy can go out first. So there's a guy that monitors the queue, the high priority queue, the medium, and the low priority queue. And if the high priority is filled, it fills it in there. All right. And you go into the high priority depending on the bits that are placed on the packets, the special, there's a special field on the packet or the frame, by the way. You put a number in there depending on what that number is, then you are placed in one of those queues. Sorry. You can actually configure those bits depending on the packet. Uh, we'll see if we can do some of that in our class activity. We'll talk about that when we get to class, though, if we're able to do that. All right. Anyway, so we can set up. You want to make sure you do that because you can take care of bandwidth, congestions, delay, and jitter. So I want to make sure you understand what each one of those mean. The bandwidth means is the maximum amount of data that you can send. Okay, so if you have an application that's sending a lot of data, it needs to send a lot of information, like a video, maybe it needs a bigger bandwidth than voice. If you're doing a telnet session, it needs very small amount of bandwidth, right? You don't need a lot, because you're sending very small amount of data back and forth. Congestions, the actual day, if you reserve a certain amount of bandwidth, then you'll guarantee like a certain speed for a specific application that would be better than just hoping when I get to the highway, for example, that there's no traffic. So you definitely want to guarantee some traffic for the applications that are delay sensitive. Congestions is when there's traffic. That's what it really means. So when there is traffic, of course, video and voice could have a lot of problems with that, and you'll lose the quality of the video. You'll start getting really poor picture, delays, and frames are going to be dropped. With voice, it's even worse. Voice, you can't hear the other guy on the other end. And if there's a lot of delay, you get cut off as well. Delay means packet not reaching the destination. Sometimes we call that latency. So not reaching the packet to the destination on time. Jitter is when you have variation in the delay, different times. You can compensate for delay if you find out exactly what the delay is. You can move up. Let's say if you're, if we're all coming to class 10 minutes late every day. So what we do is we move up the class 10 minutes. But if it varies 5 minutes, 10 minutes, 15 minutes, 20 minutes delay, it's a little bit more difficult to compensate for that. Packet loss is when you lose your packet, and if you lose your packet, that could be an issue. If you lose in voice, there is a technique that if you lost your packet, you can actually figure out what the packet is going to be and make it up. As long as you are within 1% of packet loss with voice, there is really no noticeable audio problems. If it goes above 1%, then it's an issue. With Same thing with video. If it's less than 1% video lost, you can tolerate that. Anything above that, it could be also an issue. The delay has to be for voice 150 milliseconds. If it's anything higher than that, then it becomes a problem. For video, it's 400 milliseconds, as I remember. 400 millisecond, you can tolerate 400 millisecond delay in video. Anything more than that also could be an issue, and then packets can start getting dropped, and then you start having video issues. All right, please write this down. So I want you to make sure you understand all of this. So when you are trying to create quality of service, you can set the bandwidth to reduce congestions, to take care of delay and jitter, and also make sure that you don't have a lot of packet loss. So that's why you want to set up your system. ISPs on their end, they have techniques to make sure that if you have a video or a voice packet that it's going through, that they're going to have priorities. Okay. So for example, voice video, like we discussed earlier, you want to have smooth, benign, nothing being dropped, no delay whatsoever if you can. Like I told you, 150 milliseconds is the maximum delay that it can have. You need about 30 kilobyte of bandwidth. That's really it. So look at 30 kilobits per second when it comes to voice. That's all that the bandwidth it needs. So that's for voice. When it comes to video, pretty much the same thing. You need about close to 400 kilobits per second for video. If you're talking about high def, you need about 19 megabits per second nonstop. But if you compress it using MPEG-4, MPEG-2. If you compress the video using MPEG-4, MPEG stands for the Motion Expert something group. I forgot. Motion Picture Expert Group. That's what it is. Anyway, so if you compress the video, you can actually get it up. All you need is 9.8, megabits per second to have a full HD video streamed nonstop without any delay whatsoever. So that's great. For data is really you can tolerate almost nothing. You can have you're downloading a file, for example. It can go in very fast on the good days. It's really a best effort technique when it comes to data, or it can be it could take hours. So it can tolerate a lot of drops. Okay, so there are queuing algorithms. So the first one is first in, first out. So please write that down. That's one algorithm technique. First in means when data comes in to the buffer, the first guy that comes in, the first in, he's the first one served. And you go out. Simple. Second queuing technique is called the weighted fair queuing. Write this down, and I want you to also write the description of the WFQ. WFQ, what you do is you classify the data. Each piece of data, depending on who you are, you'll be placed in a class. And each class will have either high priority, medium, normal, or low priority. And when you come in, I look at the number that's stamped on you, and I'll put you in your queue, in your place in queue. If you're high queue, in the high priority queue, medium, normal, or low. All right. The problem with this is if you have telnet session and it's doesn't require a lot of bandwidth, and there is maybe a video that's taken a lot of the bandwidth. So these guys are going to have to wait. Nobody can telnet, even though I just need a very, very little amount of bandwidth. And if you're watching a movie, you can probably never be able to telnet, depending on the movie, if it's high def, for example, right? So, because everybody, depending, that's what they waited means. Everybody, depending on how big you are, you go into a specific queue. Now, the only problem with that also is you need to look at the actual data. So if the data is encrypted, becomes a problem, WFQ. No tunneling and encryption because the feature modifies the packet content information. All right. So there's another one, the class-based weighted. So what I can do is, depending on what this is, the third one, we can actually take care of we can take the WFQ, the weighted queue, and we placed it into classes, class one, class two, depending on what you are. So this will make it a little bit easier. We're going to assign bandwidth and wait maximum packet limit. So if you are a video, for example, that's going to eat up the whole bandwidth, we're going to say, okay, you have a maximum of, you can use the bandwidth for this certain amount of time. So if, let's say, a telnet session comes in, we could tell them, okay, you can go quickly, and we'll let the video take over. So the class-based makes it a little bit easier, so nobody can eat up the bandwidth for the whole time. Okay, so these are the most widely used type of queuing algorithm. Okay, and there's the low latency. So there is no strict priority queuing. Actually, so what they do right here is the priority frames. What they could do is when you come in, if you are, let's say, telnet session, they put you in the priority. And if you're not, you go into your other classes, the class-based. So or if you are voice, for example, you go up here. Everybody else comes down here. Then you're placed up into classes. So for example, this is to make sure we don't eat up the bandwidth with anyone. So if a voice comes in, he goes up first. And if data, they go down here into classes. And let's say if it's video and you can tolerate some delay, he'll be class one in the class based. But if it's voice, it goes always into the priority. This is actually the most widely used queuing algorithm, although it works with the CBWFQ, the class-based. That's to give you the LLQ. So write also this down, and I think this is the last queuing algorithm that there is out there. These what are being used by the service providers to send you the data to your either organization or even home. So LLQ allows delay-sensitive data such as voice to be sent first. So this is definitely the one that you want to go with. Excuse me. Okay, so now let's take a look at some QoS mechanism. There is the best effort, number one. Not really. There is really no QoS with best effort. I'll do my best to send the data out to you when there is, excuse me, when there's no congestions, and if there's congestions, what can I do? Everybody has to wait. We'll do our best. There's the integrated services and the differentiated services, which we'll discuss in a few minutes. So when it comes to integrated services, you're going to be able to speak with, well, routers talk to each other and they reserve bandwidth all the way to the destination. And then the voice, for example, or the video that is sensitive to delay can go without any delay whatsoever. So we want to make sure we clear the road before we get to our destination. Differentiated services, but the problem with integrated services is because you are reserving the bandwidth, that's going to really eat up a lot of and it's less efficient. It's going to eat up a lot of the bandwidth that other applications may need. So that can slow down things dramatically. but that will guarantee packet delivery. No packets will be dropped, almost zero delay. So you can watch the Super Bowl without any problems whatsoever. But everything else will be limited. Differentiated services, what they do is you can set up classes. Depending on which class you are in, then you will be sent out. It will use some of the integrated services, but it's much better and much smarter to getting to the destination. It will use techniques and it will tolerate a little bit of delay, but it's a lot more efficient. All right, so the three different models I want you to write: best effort, integrated service, and the differentiated services. Um, Here's the benefits for the best effort and the drawbacks. If you want to write those down, that's really up to you, not required. But here we go. Let's get into the integrated services. So I said to you earlier that let's say the sender, what they do is they tell the guy right here, I want you to set up a specific amount of bandwidth because let's say on video, and each one of them will reserve bandwidth, and no one else can use, and then we'll just go right through to the destination without any problems whatsoever. So that's nice. That would be really nice if you could do that. But the problem, like I said, bandwidth is not unlimited. So if you reserve a certain amount of bandwidth for some traffic no one else can use, then you got problems. It's like taking one lane in the highway because there's the president or some big guy wants to use it for a certain amount of time. That's going to create traffic for all the other lanes, right? And no one else can use that lane. So that's what really the integrated services do is they open up the lane from the source to the destination, going through many different cities that no one can use till that person goes through, right? So it's nice for that person because he notices no delay whatsoever. Everybody else, um, they're going to have a tough day, right? And if you cannot open up the path, by the way, as it says right here, if one of the routers says, "Hey, listen, I can't. There's too much traffic here, and I'm too busy, and I can't open up a lane," so the guy will never leave, of course, right? He stays home. As therefore, if it's voice or video that you're trying to connect, um, you'll be noticed that there's no connection, right? No, because you don't have enough bandwidth. Okay, for differentiated services, you can have what you could do is you can classify and manage the network depending on what you could do, depending on what you're trying to send, and we can provide guarantee, some sort of guarantee uh, connections for voice and video. It's almost guarantee, but it's still it's a lot more efficient. Okay. All right. Now, when it comes to implementations, the first thing we really want to do is we want to avoid packet loss as much as we can. So depending on how much can we tolerate packet loss, it all depends. Like I said to you earlier, it has to be less than 1%. With voice, you can make it up pretty much. If it's below 1%, you can sometime make up the voice packet. And even if you lost it, there's no big deal. With video, also less than 1%, you can tolerate less than 1%. But otherwise, you got big problems. So how do we avoid packet loss? I want you to write, these are the QoS tools to avoid packet loss. I want you to write those down, and please write the description of each. So when it comes to the first one, classification and marking. So what you do is you are going to mark each of those packets that are coming into the network. You classify them and you mark them. So you're setting up, just like we talked earlier, classes on who can go first and go second. So if you are a voice, you're going to be marked and classified. If you're higher priority classification, you have the highest priority and you get out the door as quickly as possible. Um, when it comes to congestion avoidance, you want to make sure that there is no traffic. So everybody has, you can reserve bandwidth if you to make sure, open up the lane and open up the lane and make sure no one is, traveling on that lane. Or you can use the WRED tool, which we'll talk about. For example, if you are a packet that is very small, um, we can drop you off. So some packets, when there is traffic, we'll say, okay, you're not using the highway today because there's somebody important that's coming in, so you're not even going to travel. You drop them off way ahead of time. You don't even send them. Okay. Or you can use the congestion mechanism tools that we've talked about, the class-based weighted fair queue or the LLQ algorithms. So when it comes to classifications, that's the first one. You can classify them at layer 2. Ethernet can be classified. Um, if you remember when we talked about VLAN tagging, on the trunk, we tag every single frame that's getting on the trunk with an 802.1q number, VLAN number, right? Remember with the internet VLAN routing, and that number goes right in just after the packet, and where if you really know the details, and there's another field on the frame that says um, the length that indicates the length and the type of packet that's inside the frame. So you move that and you put a tag in there. That's what the 802.1q standard says. Put the number in there. Now in that tag, there's a 3-bit number. You can use it. You can use it also for tagging for quality of service, and that's the 802.1p standard, right? So you can use 3-bit number in there to indicate the priority of the frame. Um, you can also do pretty much the same thing with the 802.11, the 802.11, the Wi-Fi. There's a 3-bit number on the frame. You can use that. And the MPLS, there's a 3-bit number. With IPv4, there's a 3-bit number or a 6-bit number. Actually, there is a ToS number, which is an 8-bit number that's usually used. But it's pretty much used. This is the old IPS uses the integrated services, a 3-bit number for the integrated services. But now we're really using the differentiated services. We use 6 bits, which can give us a lot more choices or classifications. Okay. Before you classify and mark the bits on the packet or the frame, you can use layer 2. You can use ACLs or class maps to identify the packets. Who is going to have? How do you put in how do you actually configure those bits? Okay, so maybe we'll practice some of this in our class activity. I'll dig up some exercises, although we don't have any packet tracer exercises to really implement any of QoS. But I'll see what I can do to dig up some exercises that we can actually do some configuration, maybe with classification and marking. We'll see that. All right, so here is the Ethernet frame. This is where the actual 802.1q frame tagging goes in, and we'll use that priority number. This is the actual VLAN ID. We'll use these 3 bits, the ToS number, class of service right here, and that's the 802.1p. We use these for on the Ethernet frame to set priority for the frame itself. At layer 3, you have 8-bit number. 6 of those bits are for classifications, for the differentiated services code protocol, and the last 2 bits are for ESN. So these 2 bits are going to indicate, excuse me, to tell the routers up ahead that that these the, that the this packet has been configured for priority, and then we'll look at the code. Depending on what your code is, you're going to be set to either, high priority, low priority, or medium priority, and you're going to be in a specific class. So the first, for example, there is the assured here. In fact, let me go in here, and I took some notes. If I'm not mistaken, we'll go all the way to the bottom. And let me see, when it comes all the way down, yeah, there you go. This is for marking the 802.1 queue. When it comes to in here, you're using those 8 bits. So we have 6 bits that can offer 64 possible different services. So the ECN number, those 2 bits on the right hand corner that I was talking about, that's called the ECN, the extended congestion notifications, that can be used to identify to tell the routers to mark the packets instead of dropping them. So don't just, they're going to make sure you mark it, don't drop it, depending on what those bits are. I have a list of all the different possibilities of what the ECN number is and what the DSP number is. The differentiated services code point, it's called. So those 6 bits on the left-hand side, the DSP, they can be broken down into 3 categories: the best effort, expedited forwarding, and assured forwarding. So please write those 3 things down: the ECN number and what it is, and for the DSCP, the 3 categories are best effort, expedited forwarding, and assured forwarding. If the default for all IP packets are best effort, of course, so this is really no QoS. But if the first 3 bits in those 6 bits of the differentiated services are 101, that means you are in the expedited forwarding, and this is only used for voice. You go high priority, right? Cisco says if you see 101 on the first 3 bits of the DSCP, then it's an expedited forwarding, and he goes to the highest priority. That's what it really means. Okay, you go to the top. You've been classified. And the others, if it's not, then you are placed into different classes. So, for example, if you are 011, that means you are in class 3, and 10 indicates that you're in class 3, and if you're in class 3, you have medium priority, right? That's it. 0 is always there, that last bit. And that's really what it comes down to with the DSCP. Going back, and let's continue. So that gives you a little bit more details. The implementation techniques, you want to please write those 3 things down. The trust boundaries, traffic should be classified and marked as close to the source as possible. Congestion avoidance, so you want to try to avoid traffic. When the queue is below a certain threshold, there's no drops, of course, as necessary. When there is a maximum threshold that has been reached, you want to make sure that you drop packets that are not necessary, so you don't create traffic, or you can guarantee a committed information rate. So what you could do is, if you are a service provider and you see that there is no traffic at 2 a.m., you just let everybody go through. If you start noticing that there is traffic, then you start saying, okay, depending on who you are, you let some traffic drop, if let's say you're downloading a file or you're, so you know, downloading a file can wait. So you start dropping some packets because they use TCP, by the way, and when you drop the packets, the other end that's receiving will start recalling the data and says, please sending them, you know, send them again. So you can tolerate TCP connections, but and you let voice go through. Shaping and policing. Uh, what that does is for drop packets, if the packets are being delayed, they sit in the queue, and you can set them up close to each other. So you let them come into the queue, wait, and you rearrange them so they can go out the door in a smooth manner very quickly. So even if you have some, that's really you know the traffic shaping. You want to when you have jitter, you know when data is coming in at different delays, what you do is you hold them in the queue, you put them together, and you let them go out the door in a smooth manner. No delay whatsoever, no jitter. So that's shaping. You know, and you can't really unless they are marked. So traffic shaping retains access packets in the queue and then schedule them to leave over an increments of time. Policing, policing. Well, policing is applied on the inbound on the interface, depending on UR. So when the traffic rate reaches the configured maximum rate, traffic is dropped or marked, depending on what you are doing. All right, and that's it. So hopefully that gives you a quick overview. I know you will cover this in a little bit more details if and when you take a voice over IP class. And so this is really the theory of all voice over IP in real time. So, but in there you'll discuss a little bit more about the SIP protocol, the session initiation protocol, and more about the implementation and how to configure and do the actual configuration. But like I told you, I will try to come up with an exercise for a class activity on the quality on the QoS. All right, until then, keep up the good work.